So we have concluded the second chapter of my book, that is on one-dimensional search, and I'm going to review some of the concepts we have studied in this chapter briefly. So basically we started this chapter with the concept that when you do a search method in optimization, you typically consider what is known as a search direction, which we denote by the vector d, and then you find a step size, which we denote by the letter alpha, by which we move in the search direction. And this partitioning of the optimization search problem into two parts, that is discovery of the search direction and discovery of the step size, is a very important process. Then we embarked on a series of methods which seek to determine the step size, and all these methods constitute the problem known as one-dimensional search or one-dimensional minimization. We also saw that this one-dimensional search place is unimodal, that is, it has one minimum point if you have chosen the search direction properly and the search direction satisfies the descent condition. And essentially what these one-dimensional search methods try to do is they bracket the minimum point to an interval which we will denote by I. And then this interval is progressively narrowed down till it becomes very small, and we can specify the degree of smallness of this particular value of I. And the methods which do not use gradients, which we discussed in this particular chapter, are also called zero-degree methods. Now we saw that the simplest one-dimensional search is what is known as the equal interval search. And essentially this method involves moving in small equal steps until the minimum is bracketed. So this method is very robust, and to give you an example, you can start with a step size of 0.1. You can partition your domain using this step size and bracket the minimum. Then you take this new interval which you have obtained and you partition it further using step size such as 0.01. You get the interval of uncertainty here. You again partition this by 0.001 and so on. So essentially if you are writing a program, you have a loop which continues doing this till you reach your specified size, which could be 10 to the power of -8. And at this point you essentially stop this search. So this method is very robust, but of course it moves very slowly. So we see that this kind of search process where you partition the domain into a uniform grid is conceptually simple but computationally expensive. But this equal interval search is often used as a safeguard technique where more efficient algorithms are used, such as quadratic search or cubic search. And what happens is if you have any chance of those methods becoming ill-conditioned or not converging, then you can switch your method to this particular method and then you can converge without any problem. So these safeguard techniques are built into many professional software. We next move to the concept of golden section search, and these search methods are based on something known as the golden ratio. And we saw that this number has some interesting properties in number theory in terms of the theory of line segment and also in terms of the Fibonacci series. Now, the basic premise of the golden section search is that it progressively takes larger steps as it moves rightward, and then the minimum is bracketed. Now, once you have bracketed the minimum point, you actually start reducing it, and this is where you use the golden ratio to bring down the particular domain which you have selected, and you keep progressively reducing it, and you keep doing it till you reach a certain level of precision which you have prescribed to your method. So again, it could be 0.1, it could be 0.001, it could be 10 to the power of -8, depending on the level of discretization which you need. Now, typically the golden section is going to be faster than the interval search, and it is going to converge relatively faster. Now, the next method we looked at was the polynomial interpolation method. and this method is also used in various software packages. Now, in this method, what you do is you start out with a method such as golden section for bracketing the minimum, and then you progressively reduce this interval using quadratic approximations of the function. And we discussed how you essentially narrow down this interval, and you keep doing this till again your goal of 10 to the power of minus 6 or 10 to the power of minus 8 is obtained. Now, several times the polynomial interpolation method can suffer due to ill conditioning, and this happens because the fits of the function which you are generating may not be very good mathematically, and there may be some division by small numbers and so on. So in such cases, you can switch to any classical method such as golden section or interval search, and these are again a set of safeguard techniques. Now we also saw that the cubic functions are probably better than quadratic fits in many cases and are often used in computer programs because they will generally fit a function slightly better, but they may also be slightly more prone to ill conditioning problems. Now, there are many situations where you do not need to do a very precise one-dimensional search, that is something like 10 to the power of minus 8 level of convergence and so on. In such cases, you can use certain rough methods which are broadly classified as inexact line searches, such as the Armijo's rule. Now, in this Armijo's rule, you use a sequence of line which essentially intersect with the function, and you find a reasonably large step size which reduces the objective function. Now, one more way to do a rough search would be to use a coarse grade. So you could use a golden section method with the convergence criteria of 10 to the power of minus 1 or 10 to the power minus 2. And again, that would be quite efficient, and you could then move on with your calculation of the search direction beyond it. So like I mentioned several times, there is a trade-off between how much time you want to spend for one-dimensional search and how much time you want to spend trying to discover the appropriate search direction. Now, you could also combine different methods of 1D search and you could form hybrid methods. So we have seen that how the golden section could be combined with the quadratic search. You could combine quadratic search with a kind of cubic search and so on. So again, this is a very fertile field, and there are various possibilities in terms of discoveries of method where you can combine different methods and so on. Now, there are certain situations where you actually have the gradient there for you, and this could be because gradient is being calculated using some procedure such as a sensitivity derivative calculation, or the gradient from the starting point was there for you, and in those cases you can also use the gradient information and you can develop some methods which use gradient information. But the methods we have studied in this chapter do not use gradient information. So one advantage of that is that they are going to be relatively robust, because whenever you are taking gradients, it could be possible that the gradient may become very small and you may have some kind of problem. So this culminates the lecture here and culminates chapter 2 on the one-dimensional search. And the next chapter we are going to look at gradient methods, where we are going to look at important methods such as the steepest descent method, the conjugate gradient method, and some of the variants of the conjugate gradient method and the steepest descent method. And we are also going to spend a lot of time looking at rates of convergence and some of these issues. So again, I hope you are enjoying these videos, and please stay tuned to my channel and subscribe if you have not done, for staying tuned to more videos on these topics. Thank you very much.